Okay, so the very beginning of this video has those three practice AP multiple choice questions. So, I'm not like I have all the solutions worked out. So, if you want to pause the video, do those first, then unpause the video. Here are the solutions. For number one, I got A. So again, you can see the solution on the right. So feel free to pause the video if you want to just double check the work. For number two, it's E. And you have to be really careful because we get in the mindset of seeing reciprocals, right? And we have this antiderivative that we know the antiderivative of 1 over x, right? The antiderivative of 1 over x is ln x, absolute value, plus c. And then we start to get into this mindset of it, well, anything, right? Anything that's a reciprocal. That's ln of natural log of x cubed plus c. And that's one of the most common things on the AP exam, this universal application of ln. But it only works when it's just 1 over x. Think about like the power rule doesn't work for 1 over x, right? If you try to do x to the negative 1 and you bump it up a power and divide by that power, no bueno, right? That doesn't work. So the ln is the answer only when it is just 1 over x. But as you can see in my work over here, that 1 over x cubed, that can be solved using a power rule. So be careful of that. Like every year we get feedback as AP teachers saying the universal application of ln is a common mistake on the AP exam. So good to know and watch for. And then here, a nice U substitution. We don't know how to integrate ln. So when you see ln in your expression, that should be your U. Okay. Eventually, we're going to learn how to integrate this, right? Ln x. But right now, we don't know. We need a technique called integration by parts, which is nice. It's great. It's awesome. But we don't know that just yet. Okay. Now, some examples, like on the right column here, we're going to need to use a U substitution to get us ln as our value, or as our antiderivative. But right now, the degrees of the numerator and the denominator in this case are the same. So when I let this be my U, I don't get 1 degree lower. And that's because this fraction is not in proper form. This rational function is not in proper form. So, moans and groans if you like, but we have to do long division to simplify that. So I'm going to go ahead and get an equivalent expression first. And it's not too bad, this one. 2x plus 3 goes into that expression twice. So 2 times 2x is 4x. 2 times 3 is 6. And don't forget we subtract. So I'm going to use these parentheses. So 9 minus 6 is 3. So that's equivalent to doing the integral of 2 plus a remainder of 3 when divided by 2x plus 3. So now I actually can do my integration because I can let the denominator of this be my U, and its derivative would just be 2, and I can fix the 3 to make that a factor of 2. So I'm no issues with that. And then when we integrate to 2, it's just going to become 2x. So I'm going to do a U substitution just on the right side, really. So like right here, I'm going to let U equal 2x plus 3. So its derivative is 2 dx, and we need a 3. So if I multiply this by 3 halves, so 3 halves du, 3 halves of 2 would give me my 3 dx. So I'm going to integrate, like the integral of this one is just 2, I could say like dx, plus this one is 3 halves 1 over u du. And I kind of like I separated that because this one's in terms of u right now, this one's in terms of x because it didn't need a u substitution. Its antiderivative is just 2x. This one is 3 over 2 times the natural log of the absolute value of u plus c. And then now we can go back and say, well, what was u? It was 2x plus 3. So 2x plus 3 over 2 natural log absolute value of 2x plus 3 plus c. Again, you could take the derivative, check your work. You'd have to add your common denominator and to get to that value, to that expression right there. And another thing too, these coefficients, I think I mentioned in the last video, you could bring that up and have it as a power. I would just recommend leaving it here. It's fine. And in any time you don't see a function that has a proper integral, like this one, right, we have to do long division. Now, it's deceiving, or it's deceptive, I should say, that I almost want to be able to factor this. The top factors, you could factor a sum of cubes, but you can't factor a sum of squares, at least across the reals. And so anytime, again, like your u, like we want this to be our u, but its derivative would be a linear function, which I wouldn't get up here. And I can't let that be my u because I can't have a du in the denominator. So I'm going to have to do long division. So if we do x squared plus 1 divide into x cubed, and I probably should keep track. I've got 0x squared, 0 x's, and then the 1, just in case I might need that. So x squared goes into x cubed x times x squared is x cubed plus x. We subtract. So obviously the x cubes cancel, 0 doesn't affect us, but we get 0 minus x, so negative x, and we drop down our 1. So now what I have is, right, so now what I have is this when divided by that. So this is equivalent to x plus negative x plus 1 when divided by x squared plus 1. And this is what I want to integrate. Now, I'm closer. I can certainly let this be my u, but then its derivative is 2x, not 2x plus 1. So I'm going to do another little sneaky trick here, and then I'm going to be sad because I know where this is going, and we don't know quite enough just yet, but we'll get there. In about like 2 videos, we'll be there. But here's a trick that we would be able to do at least part of it. I can break this up to 2 separate fractions as if I were undoing finding a common denominator. Okay, so, right, because those 2 fractions, like this fraction and this fraction, if I would have seen them, I'm like, oh, they have the same denominator. I'm going to put them together, and then there's right there in the numerator. So I'm going to split them, because when I do that, that now allows me to integrate that middle term. I can now let u equal x squared plus 1, which means its derivative is 2x dx. I'm off by a factor of negative 1/2. So negative 1/2 du would be negative x dx. So I can integrate this. That's just going to be the integral of x with respect to x. And then this will be plus the antiderivative of negative 1/2 1 over u du plus the integral of whatever 1 over x squared plus 1 dx is. We're going to hold our thoughts on that for a second. Well, this just x squared over 2. This becomes negative 1/2 natural log of absolute value of u. And then we have a plus c somewhere. Plus c, and it doesn't really matter where we put that, plus still this antiderivative here. And like I said, I'll be honest with you, I didn't realize this was in this example, but it's good. It's leading us to what's up and coming still. Let's go ahead and get rid of at least this u, which is x squared plus 1. So we have 1/2 x squared minus 1/2 the natural log of x squared plus 1. Notice I didn't really use absolute value because x squared plus 1 as a quantity is already positive. Plus c plus this thing, right? Plus this integral of 1 over x squared plus 1. Now, at this moment, this we don't know how to do. But when we get to the next section, this is like the perfect integral of all things, is the arctangent of x. So at this point, we haven't learned this just yet, so you'll have to trust me on this part. And I promise you, I hope I won't have any of those in tonight's homework. But eventually we're going to learn, and this is actually an quote unquote easy one. They get much tougher. So arctangent of x and then plus c. So other than that arctangent, the two tricks, obviously, or not two tricks, the two strategies are to make sure you reduce your function so that the degree of the denominator is the highest power. So if you see the numerator higher, divide out. And then if sometimes you might need to split a fraction up, like I did here. So, and then, like I said, we will get there. I promise. This is up and coming, and how it's related is kind of cool. And so we'll prove how those functions are there. Yeah, if you have any questions, just go back and double check. And otherwise, just keep working on the homework.